Finally, we get to talk about atoms. Enough numbers. Well, we'll talk about numbers, but we get to talk about what's in an atom. And you probably already know. Protons, neutrons, and electrons, and not croutons. Croutons are not a subatomic particle, but they're delicious. Let's go talk about atoms and isotopes right now. Ni hao, everybody. Ni hao. Mike here, and today we're going to break in to Chapter 2 of the OpenStax textbook, or what is commonly Chapter 2 in most other textbooks. We're going to talk about the nature of atoms. We're done talking about numbers today, except for simple numbers, so we'll give you a little break from that. First, let's talk about how an atom is put together. So we've got two parts. We have the nucleus, as you can see, and then we have the electron cloud. Now, I cannot draw this correctly, because if this was to be to scale, the nucleus would have to be a blueberry. That's an actual, what's we call in science, a blueberry. And however, this electron cloud, first of all, I drew it as a sphere. It can be construed as sphere-like. It has distinct boundaries. When I was drawing it, my hand shook and made this little dip there, but I kind of like that because the electron cloud is sort of diffuse. You can only kind of talk about where an electron will probably be, and 95% of the time it might be in something like a sphere. But then once in a while electrons do weird things and go outside of that. And then so we just talk about where the electron probably is, and we call that the electron cloud. Here's the thing, the electron cloud compared to the blueberry would be the size of a stadium. So just for reference, that would be like, a stadium. This would be like a blueberry or a pea, if you don't like blueberries. But who would not like blueberries and like peas? I don't know, sorry. Hey, well, how do they know? Okay, well, I will tell you a story of Ernest and the golden foil. Once upon a time, there was a man named Ernest Rutherford. He was from the same place where Lord of the Rings was filmed, but that's not really all that important. What Ernest Rutherford did was decide to understand better the nature of atoms by pounding out a very, very thin layer of gold foil. I should probably show you a better picture of this. So, the reason they used gold is because gold is very soft and malleable, and you can pound it out to very, very, very thin. So what they did was they put some alpha particles in a lead box, and what will happen is alpha particles are emitted. They're actually particles. We'll talk about that in general chemistry too, but they're emitted in all directions. But if you put them in a box with a little slit in it, you will make a beam of alpha particles. And so the skeptical person might say, well, what would happen? And well, actually, what did happen was a little bit of everything. What does that mean? That means that some of the alpha particles went straight on through, and they hit this photographic film and left an impression. Silver chloride, if you hit it with enough energy, photographic film doesn't need visible light. It could use all sorts of different things to make it have a reaction. So some went straight through. Some had their path altered slightly. Some were all out, just didn't get through it all, and it bounced right back. And so I think I should have drawn the foil was like all around, like a better picture that I probably should show you right now. what happened is, since a little bit of everything happened, particles going straight through, particles going kind of having their path altered, that tells you that if you look close enough, atoms are not homogeneous. The nucleus is much, much more dense than the electron cloud, which is much, much more diffuse. So, and then think about that. The electron cloud's diffuse and it's the size of a stadium, but the dense part's the size of a blueberry. And so the alpha particles that went straight through, they must have gone through the very, very edges of the fringes of the electron cloud. And then the thing that got bounced right back, the alpha particle that got bounced right back, must have hit smack on the nucleus. And so that's the proof. And look, folks, we can't see atoms. If you could see atoms, you'd be working for the government in secret. But we can't see them, so we have to trust these kinds of methods. And then someone with an imagination has to say, I'm going to set up an experiment like Ernest Rutherford did. And that's what we know today as the sort of nature of an atom, is that you got a dense part and you got an electron cloud part. Now, let's talk about the very, very specific properties of everything in both of those parts of the atom. So I've made a little chart here, and we're going to talk about the three components of an atom: protons, neutrons, and electrons. So let's talk about their symbol first. Protons. Now, you ever forget? Pro, positive, like pros and cons. P plus. We'll talk about that. That's its charge. A neutron is neutral, doesn't have a charge, so it's just a symbol N. And an electron is negative. So protons and electrons are oppositely charged. Now, I don't want to blow anybody's mind here, but you know, they could have just called electrons positive and protons negative, or they could have called the thing that goes around the electron cloud, they could have called it the proton cloud, but they're just opposite, so they attract each other, and that's why electrons don't go flying off. And then using symbolism, I put the blueberry where the nucleus is, because I don't need that anymore. Good antioxidants. I'm very antioxidant. No oxidants. Okay, so, oh my goodness, you know what I meant, nucleus. I was trying to write while I was, nucleus. Good, I get to do it over again. And I still did it wrong. Nucleus. Mike, I'm a little tired, folks. And I put my blueberry in the wrong place. Okay, you needed to know I was human. So, the electrons in the electron cloud. Sometimes I think ahead to the next step and then I goof up. So, the protons and the neutrons are in the nucleus. You know, neutron sounds like nucleus or whatever, but you'll get to see electron cloud sounds like electron, so you probably won't get those two confused. Plus one is the charge of a proton. Remember, pro, positive, like pros and cons. Nothing is the charge of a neutron. They're neutral, and electrons are -1. Now let's talk about this mass issue here. Now, I think in when we were talking about scientific notation, I told you that this is the mass of an electron, or a proton, excuse me, and then you saw the crazy, crazy small number, like 1.67 times 10 to the minus, 27 grams. So you know what we do? Just like when someone needed to know the distance of something, and we realized that we could kind of heel-toe distances to figure it out, you know, we said, hey, let's just come up with a unit called a foot. And it was some king's foot or something, of course. It's always a king something. But, and he's like, this shall be the foot. Well, someone said this shall be what we call an AMU, which is about the mass of a proton. And a neutron is about the same mass. Electrons, on the other hand, are very, very small compared to that. 0.005 something AMUs, a 200th of an AMU. And so I'm going to do, folks, what we do, squiggly equal sign. Squiggly equal sign means about nothing. Why about nothing? Doesn't it have mass? Doesn't it matter? Yes, it does have mass. Yes, it is matter. But it's kind of like saying, well, I got to go do a weigh-in for my keto club. I just made that up right there. And then you're like, well, I weigh 165, but you know what? My hair was wet. That don't matter. You know, that does matter. Yeah, it did make you heavier. And you know what else makes you heavier? When you go like this, you just breathe in, you just got heavier. But not much. So what we're going to do from now on is we're going to call the electron's mass negligible. It does have mass, but we're going to say it is negligible. Not really worth bothering with. When we talk about what the mass of a whole atom is, we're going to ignore the electrons. All right? Yeah, we're not going to ignore their charge. That's important. So how do we communicate atoms to other people? Okay, I took fluorine. It's going to be our very next example. We're going to talk about exactly what is in a fluorine atom. Now, we have the symbol, because we need to sort of personalize these things. And actually, some of the elements had very, very unique places where the symbol and the name, they have like Greek names and whatnot. Fluorine, you got me, folks. I'm not much of a historian. I just told the story of Ernest Rutherford, but I don't remember where fluorine came from in terms of its name, but we give everything a symbol so that we're not, it kind of personalizes it. Like helium was discovered in the sun, from Helios, the sun god. So everything has its own unique place where its symbol came from. And I'm going to tell you that right now the symbol is pretty much the same as the atomic number. So if something has a different atomic number, it's a different element, and therefore a different atom. So the atomic number is kind of like the government doesn't care that your name is Mike Canistero. I use myself as an example. But, the government, pretty much my name is my social security number. So if something has an atomic number 1, that's hydrogen. Atomic number 2 would be helium. So these two are really sort of redundant. One way to kind of personalize it. The mass number is the mass of the whole thing in AMUs. So for something like this atom of fluorine, this is going to be everything with mass, which will be the number of protons plus the number of neutrons. So apparently fluorine has 19 AMUs worth of stuff in it, which could be, now it's going to have to be, we'll talk about what it's going to be. Atomic number is going to be very, very specific. This is the number of protons only. Think about how boring the world would be if we just said element number 9 with 9 protons. That's why we give it the name fluorine. And then, by the way, there's different kinds of atoms in an element. What? No, those aren't the same term, atom and element? No. An atom is a specific particle that has a certain number of protons, neutrons, and electrons, but the element, fluorine, is just all the atoms that have 9 protons. So you can find that different kinds of atoms can reside inside of the umbrella of what we call an element. And in some cases, they have different mass numbers, but the same atomic number. And we call those things isotopes, and we're going to talk about that next. And then when we talk about an atom in writing, we give it the name of the symbol, we give it the name of the element, and then we put a number after it. So we say fluorine 19, or carbon 14, or, hydrogen 2, but sometimes those get nicknames like deuterium. Anyhow, funny story is I'm bad with vowels, and I spent a good part of a semester spelling fluorine wrong. And I got the U and the O mixed up, kind of like I did with nucleus up there. And I ended up calling it Fluorine. You know, the students in the back were laughing, and I just thought that was funny. But it was Fluorine. I was writing it. It sounds like some sort of strange baking ingredient. So let's really dig into what's in an atom, and let's use fluorine-19 as our example next. Fluorine-19. The question is, our task is how many protons, neutrons, and electrons is in that atom. Now, do you notice I didn't write the atomic number? That's because if we use our friend, the periodic table of the elements, specifically, let's go locate exactly where fluorine is, right there. Focus, focus, right there. You will see that every periodic table tells you a mass number and an atomic number, specifically atomic number. So even if they don't give you that, you write it in, you say, hey, fluorine is always atomic number 9. So therefore I know right off the bat, filling in this chart, it's got 9 protons. That's the easy part, folks. That has a mass of 9 AMUs. That has a charge of positive 9. Now, you see where I wrote total down there? That's where I'm going to help solve this puzzle. Because the mass number is 19, I know that the total mass is going to be 19 AMUs. And so, I can fill in the piece of the puzzle here. Pieces of the puzzle are that I don't care how many electrons I got. It's going to be 0 AMUs because electrons, as we previously stated, weigh nothing. So then think with me, we got to have how many neutrons? Got to be 10, folks. 10 neutrons. Because the total mass number was 19, and so we got 10 neutrons. What's the charge of 10 neutrons? 10 times 0? Nothing. Now, I'm going to tell you right now that the total charge of any atom is always 0. So, atoms have charge of 0. Atoms have a charge of 0. If it doesn't have a charge of 0, it's no longer an atom. It's something called an ion, which we will talk about in another lesson or two. So, let's fill in the rest of the puzzle, knowing that we got to have a charge of negative 9 to make a charge overall 0, which is 9 protons and 9 electrons. So the answer is we got 9 protons. And we got 9 electrons, and we got 10 neutrons. It's not the same order as what I wrote up above, but you get the idea. Now, that was doing it the hard way. Let me tell you the easy way. We go write it in that specific notation like you're supposed to do. This number right here on the bottom, of course, is the number of protons, but if it's an atom, it's going to be the number of protons and the number of electrons. So we got 9 protons and we got 9 electrons. There's 2/3 of the whole problem. Subtract these two numbers. That's where the extra mass came from that wasn't a proton and an electron. That's the number of neutrons. So 19 minus 9. There you go. That's the easy way. But you see, if I just coughed that up to you, you wouldn't have such a deep understanding of it. So I did it the hard way, and now you don't have to do it the hard way anymore, because now you understand the deeper meaning behind the hard way. So here we go. We're going to do cobalt-60. Uh-oh, don't got an atomic number. What do I do? Well, reach for this. Our friend, the periodic table of the elements series. Right there. What's that saying? Right there. Cobalt's atomic number 27. Therefore, I've got 2/3 of this problem already done. 27 protons, 27 electrons. 60 minus 27, 33 neutrons. Okay, folks, we're almost done for today. What I'm going to talk about next is the mystery of why we look in the periodic table. Let's take boron. Focus, 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 boron. Boron. You're probably like, I'm already getting my boron. So what's up with the mass number in the periodic table? A lot of times they don't land on an even number. What was that, 0.81 of an AMU, 10.81? How's that possible? Did they split a proton? No. Turns out that is an average, and we're going to talk about that next time. But it turns out there are different atoms within an element. Those are called isotopes. Boron has 2 isotopes. Let's talk about isotopes for our final leg of the journey next. There you go, folks. This is the definition of an isotope. Isotopes are atoms that are the same element but have different mass number. Now let's think about why that could be. Could it be because they're a different number of protons? No, they wouldn't be the same element. Could it be because they have different number of electrons? No, they wouldn't be atoms. So it must be because they have different number of neutrons. And that's exactly why. So let's go and take a pretty exciting element, hydrogen. There are 3 isotopes of hydrogen. Now I want you to really know that me personally, I don't ever ask anybody to memorize all the different isotopes. So you could say, like, why is there 3 isotopes of hydrogen and only 2 for boron? I'll be like, don't worry about it, just is, all right? Don't worry about it too much. But if you do a little bit of digging here, hydrogen got an atomic number of 1. This guy has, let's start over here, has 2 neutrons. Remember, subtracting the 3 from the 1. And that's called tritium, by the way. Sometimes they have really cute names. Sometimes they just call it hydrogen 3 or something like that. This has 1 neutron, and then this would have 0 neutrons. And you'd be like, what? Really? You can have something with 0 neutrons? Well, just hydrogen, pretty much. There's 3 isotopes of carbon, where you got carbon 12, carbon 13, and carbon 14. And they all have atomic number 6. And so therefore, if you do a little bit of work with subtraction, higher level math, this has 6 neutrons, 7 neutrons, and 8 neutrons. And you've probably heard of carbon 14, which is what we use to date very old artifacts and bones and things like that. And Ötzi the Iceman. Yeah, and can actually, for reasons we can't talk about, determine the date of things, if you believe in that kind of thing. So what happens is, when you're looking at the atomic mass in a periodic table, that is an average. It is what we call a weighted average. So the mass in the periodic table often isn't a round number, because look at that, 12.01. What does that tell you? Well, it must mean that out of all the different atoms of carbon, there must be a hell of a lot of it that is carbon 12 and hardly any 13 and 14. And you'd be totally right. Same thing with hydrogen. If you were to look at hydrogen and say, hey, 1.01 AMUs is the atomic mass. Must be there's a lot of that hydrogen is hydrogen 1, and hardly any of the deuterium and tritium are their cute names, which is good, by the way, because they're both radioactive. And so that's what we're going next. What we're going to do next time is we are going to go back and forth between the percent abundance of each isotope and their atomic mass, so that you have a deeper idea of the atomic mass. And you say, hey, carbon 12, That's radioactive, right? But does it still behave like carbon? Yep, it's still like the element carbon. It just is a higher mass number and it's heavier, moves around slower. So, hey folks, we will see you next time when we get deeper into isotopes. Thanks for watching. Some of you had to, but thanks anyhow. Okay, bye.